But anyway, on with this stuff. The topic is interstellar flight. And, you know, there's some fun reasons that we've seen in the science fiction for this. And, you know, even the classic purpose, you know, to explore strange worlds and have a sex with aliens. I mean, you know, okay, come on. I mean, I can't quite see, yeah, the number of hands. But has anyone in here not ever wondered about that? Yeah, okay. Well, okay, there are more serious things, too. Yeah, okay. Get past that. Okay. The real reasons is you want to do this is so that humanity does not go extinct. Eventually, certainly 500 million years. And those who thought it was 4 billion years, well, Earth will be a crisp by then. It's like 500 million years. Photosynthesis can't happen anymore because the sun's just too intense at that point. And then, of course, as you saw in the prior talk, there's all sorts of things that might take us out quickly. But then, from another talk about abundance, how when there's enough abundance, we're less likely to kill each other. Well, we'll get plenty of abundance of real estate if we can actually do spaceflight. But, you know, that's the long-term things. But in the near term, even from the attempt, we get benefits. Like, I would much rather give humanity new frontiers to conquer rather than leaving us no other option here on Earth than to conquer each other, which we seem to be working on. The other thing, they talk here about other social structures and things like that and ways of thinking about how we can live together. Well, when you think of this in terms of world ships, of sending, you know, segments of humanity out to live essentially forever in a different context, it's a context by which you can start toying about these things in kind of a far future, not really going to affect our lives sort of way, to shy away from all the emotional, hot-headed stuff when you ask about, well, what's the population limits of this Earth, you know, contraception, and cultural differences, which are usually handled by wars. So, you know, those contexts is a way of maybe toying with those in a more impartial fashion. The other things that on there too is that when you go for interstellar flight, it is so hard, you just can't extrapolate what we already know how to do. Now, going to the moon and Mars and things like that, those are pretty much extrapolations of what we can do. It's not a matter that we can't, it's just, you know, just clicking through the details. Well, there's some things on Starflight that put an entirely different character. And yeah, I also do this because it's kind of cool and fun. Okay. So, give you a sense of what's out there. And yeah, Carl Sagan liked to say billions. I hope that's money. But that number is the number of exoplanets, meaning planets around other stars that have been observed so far. And that's a lot. And the continue they learn. And there's a JPL site, Planet Quest. If you're ever curious what's today's tally, that's it. Now, some of those numbers are unconfirmed, meaning they do take several looks to make sure they're actually seeing evidence of the planet as opposed to something else. But a news flash, just earlier this week, it was found that there are 5 planets around Tau Ceti, and at least 1, if not 2, are in a habitable zone. And also their masses, the smallest one was twice the mass of Earth, the biggest one was 6 times the mass of Earth. Now exactly what that means for their climate, how much gravitational attraction, it also is a function of how big they are radius-wise, and we don't know that yet. But yeah, so, and 12 light years away is not, well, when it comes to the size of our galaxy, is not outrageously far. When it comes to our ability to get there right now, yeah, it's kind of hard. So there's been a lot of thought into Starflight right now, and actually the Voyager spacecraft is already at the edge of our solar system. By solar system, I don't mean the planet Pluto or whichever one is now designated as the farthest out planet. I'm talking at the heliopause and the bow shock and other things like that, where the effects of our sun meet with the galactic background. And it took it 30 years to get there. And if it was heading toward Alpha Centauri, which is our nearest neighboring star, which is a little over 4 light years away. And for those who don't know light years, that means how long it's going to take light, the fastest thing we know, to get there. Anyway, if it was pointing there, it would take 80,000 years. So that means if the cavemen had launched Voyager, about now it might be reaching Alpha Centauri, and certainly its warranty period would have run out by then. These other ideas span different levels of whether you're talking about trying to do something cheap and easy, or whether or not you're trying to do something better. Now, The fusion and antimatter, they're kind of like at essentially the extreme edge of technology. Not really sure we can pull them off effectively, but they're kind of like the exchange. Then maybe we could get down a trip to Alpha Centauri in terms of decades. But if you really want to get there within short attention spans, I mean shorter than a time frame of the congressional decision-making process, you know, you have to break the light speed barrier. And that's not all. I'm going to talk about frame drives or space drives or something like that. It's not just a matter about the speed, it's a matter of the propellant. I'll get to that. Okay, now here are some things that are often not known on this. Light speed, even though it's the fastest thing we know, is actually really, really slow in terms of interstellar distances. You know, our nearest neighboring star is over 4 light years away. Our galaxy is about 50,000 light years. So to the center of the galaxy from where we are, it's about 25,000 light years. And also estimates on where the nearest habitable planet might be, you know, just a statistical one based on early estimates says, well, you might go 20 light years out before you start to get things, and the peak will be at about 90 light years. So that one at 12 light years is really encouraging. But here's the other part. When you do that estimate for potential civilizations, which the estimates span all over the place, but you get numbers like that the nearest one might be 500 light years away, or peaking more around 2,000 light years apart. The good news, bad news story is the good news is the first habitable planet we might be able to get to won't have another civilization on there that we'll have to kill in order to own the planet. The bad news is it's going to take a while before we can go far enough out where you can have sex with aliens. Right now, a major limiting factor is equipment longevity. The Voyager's 30 years. Easily, you can do many, many decades. Questionable whether or not you can do 2 centuries. And you know, some of those things we're talking about millennia or many centuries for some of those techniques. So we also have an issue of improving long-term reliability. The other thing, on the time scale of how long it's going to take us to get interstellar flight, a lot of these ancillary things that we've been talking about, transhumanism, extending the human life frame, the eclipsing of human intelligence by artificial intelligence, they're going to happen sooner, and they will affect how we choose to do interstellar flight. And that's one of the reasons I accepted the invitation to talk to this, so I could hear some of the other presentations to catch me up on what's the latest trends on those. And then there's the issue of energy. There's 3 different studies that I know of that did a fairly good job of looking at how long it's going to be before we do interstellar flight. One was based on finance, one was based on technology, and then I did the one based on energy. How much energy would it take to do a star mission, and how much energy do we as humanity have at our disposal for space missions? And when you run those numbers, it looks like we're about 2 centuries away. But that blue span there is the error range. And for those who know statistics, it's just 1 standard deviation, which means really the error band is practically all over that chart. But right now, a very crude estimate is that, well, we might be 2 centuries away, assuming everything goes as it has been going. And by the way, I mean, with the, you know, the wars and other stuff like that, will humanity be around for another 2 centuries? I don't know. I haven't run those statistical estimates. But anyway, as far as interesting things that's supposed to be happening, not too long from now, there'll start to be joyrides to space, right around the time we have the 50th anniversary of Star Trek, and I'm sure that, you know, that will be kind of an interesting time where everyone will bring out their costumes. And then shortly after that, we'll have orbiting hotels, which will also be around Apollo 11's 50th anniversary. Now, okay, for you guys that were getting really excited about the idea of a weekend getaway to have zero-G sex, I recommend that you put in your reservation for 4 days. The reason why is it usually takes 2 to 3 days to acclimate to zero-G, and there's something called zero-G sickness. So, you know, you gotta leave yourself time to get over that before you feel like having sex. Also, the other thing is the fluids in your body redistribute since you don't have gravity pulling down, and so chests get larger and legs get skinnier, which, you know, might make the, and these, by the way, are facts. Okay. Shortly after that, it was interesting, back in 1992, we looked at projections of the artificial intelligence And the numbers are still staying pretty close to what they were now. But the idea that artificial intelligence might be at the monkey level, think ahead sort of thing, is not that far off, which has a lot of implications for how much you put into space probes and the things that are going to build your Moon and Mars bases. Now, this one about what's the population limit of the Earth, it's highly debatable, but the peak of estimates seem to be around there. And then the idea that will the global warming, if we don't do anything to slow it down, will reach a point where it's just going to get worse. This is when artificial intelligence might eclipse the processing capacity of humans, which is 10 to the 13th operations per second. And by then, Elon Musk has plans to retire on Mars in 40 years. And I'm absolutely serious about that. And then the rainforest is likely to be completely gone. Again, that's an estimate that goes decades. Now, the other part of this is that I don't have much else to predict beyond that, because a lot of those things are really huge things to shake it out. But when you think about the error bands that I showed you on Starflight, you know, it might be at the best case at the end of this century. So, you know, if those things are kind of death march things, you know, the rainforest and the global warming and the loss of Elon Musk, you know, we might need to do some more exciting things more quickly. And no, I'm not referring to the Monty Python joke about the sailors on that. It took 66 years from Tsiolkovsky deriving the rocket equation to have had man on the moon. Now, rockets have been around from ancient times. When he wrote the rocket equation, what that allowed him to do is take it from a hobby and an art into engineering terms, where then you could decide or figure out how big your rocket you would need, what sort of performance would you need if you wanted to go a certain distance. That transition of going from just art and a curiosity into science, that threshold makes a huge difference. Now, the interesting thing to point out here is the idea of traversable wormholes and faster-than-light warp drives and frame drives or space drives. They entered the scientific literature, well, 1988, 1994, 1997. I don't know how long it will take after that, but these things now have crossed that line from just being science fiction notions into where there's actually enough starting work where we can ask more intelligent questions and chip away. Now, will they be ready in 66 years? Oh, well, that would be so fun, but there's the energy problem again. But anyway, with that process, that's kind of interesting there. So the other thing, the group of people that I work with, and by the way, the information from this actually comes from a whole network of people that I deal with. And one of the contrasts is most of the work that's going on now is about innovation and evolution, about, you know, making things bigger and better, you know, from Apollo to Apollo and steroids. But there's a different way of looking at the pioneering aspect, where rather than just making better sail ships, why don't we take this cool thing called steam power and stick it on a boat and see how it works? Or why don't we go back to physics now that we're seeing all sorts of anomalies where the theories that we have are incomplete, we have these other evidences that we have these other advances that give a starting point, and try and make the Starship Enterprise out of it. And this pattern of revolution and evolution goes kind of like this S-curve. And no matter what technology you have, you put a lot of work into it before you reach the breakthrough point, the lower knee of the curve. And then there's lots of refinements to get better, but eventually you're going to reach a point of diminishing returns where it's just bucking up against physical limits. Like how many sheets of paper could go through carbon paper as opposed to looking at something completely different. Revolutionary ideas that use a completely different mode, like carbon paper to photocopiers. Propeller aircraft, jet aircraft, sailing ships, steam engines, so on and so forth. So in this case, it's rockets to undiscovered propulsion physics. Okay, now this one, I just did a little collection of these were things that caught my attention I was growing up, and then after I was at least an adult and still a child. I bet that, I wish I could see hands, because with the lighting here, you guys are just kind of like this dark mass. But does anyone here recognize all of those? I don't think so. But yeah, anyway, these are for fun inspirations. There's actually stories behind each of those. But to give you a glimpse of where we really stand today on trying to, like, the process of progress, I use a scale that runs from conjecture all the way to commerce. Conjecture is like when that I want to believe thing, but you don't even know what you do and don't know. Speculation is when you're smart enough to know that difference and you're starting to play with things like science fiction. And then science is when you understand the laws of nature. Technology is when you build devices on that, and commerce is when you can actually make a profit at building those devices. And right now, these topics are at the transition of moving from speculation into the beginning part of science. The short answer is that we're smart enough to ask very specific, intelligent questions to where we can chip away at the thing. The problems are now attackable, but there's not enough progress to know if these breakthroughs are possible, or even if they are possible, how are we going to engineer them? So that's just kind of a grasp or glimpse of where we actually stand. Now, you might wonder, well, how do you figure out what to do next? And this is the method that we kind of use for this, is that on the one side of this, you have our rigorous foundations, the science and technology, which we know reliably enough that we can count on it. And then, at that edge, there are things that you haven't quite solved yet. The dark matter, the dark energy, how do you integrate the infinite quantum vacuum energy into those things without normalizing it out and things like that. And then you have your wishful visions, and you have to extract from those, what are the real critical issues and unknowns on that? And where those intersect, where those unknowns and critical intersects, that gives you the actual important problems that you can start chipping away at. So I'm going to give you an example now of, well, that's right, the example comes after. The one thing I wanted to point out, like when it comes to faster than light, warp drives and wormholes are not the only things out there. There's a whole bunch of possible ways of going in it. The quantum non-locality is a very fascinating one as well. And the main point I'm bringing out here, there is no just like one way of thinking about it. There's a whole bunch of things that have barely begun to be explored. And for those of you who don't know what wormholes or warp drives are, a wormhole is somehow, rather than having to go all the way from point A to point B, you somehow fold space where you can take a shortcut. Now when you're going through the wormhole, you're still going slower than light speed relative to the dimensions of that wormhole, but you're taking a shortcut. The warp drive is, instead of trying to move through space-time, you take a chunk of space-time and you move it. And we infer that space-time can move faster than light because when you look at the Big Bang and its expansion rate, it appeared to expand faster than light. So if you could do it for the Big Bang, why not for our spacecraft? The bad news is the amount of energy it takes to do this is enormous. And some of the early estimates would require that to do a warp drive, you need all the, take all the mass in the universe and convert it into energy, and then you might have it. Well, if you've done that, you haven't gotten anywhere anyway. The time travel paradoxes, I don't know what's the latest about that. There's been debate. You know, you can create scenarios with wormholes that you take your trip, but you've actually come back from that trip before you've left to stop yourself from taking the trip, in which case you couldn't have gone and stopped your, well, anyway, you get the idea. That those might just be a null issue. The other sticky issue is that the kind of energy you need is exotic or negative energy. And I'm not even going to attempt to try and explain this here in this context, other than to say, in general relativity, there was a lot of ideas that, well, maybe that's just physically forbidden, but in quantum physics, no, it's there. And some natural phenomenon actually do seem to violate some of the energy assumptions from the general relativity. So the issue about negative energy is being something that can or cannot exist. It can exist. Can you actually do anything that constructive with it? And can you have a lot of it? Those are unknowns. And just to give you another glimpse, when you're just talking the wormholes and warp drives, again, you have a whole branch of different possibilities out there. So this is the next level of detail into that. And there's not that many people working on it, but they are working at it in a rigorous manner. Now, okay, now this is about how you do the taking from the science fiction and starting to realize what are some of the make-break issues or things that you need to study. And the way I do this is you start contemplating your wonderful breakthrough device, my little spaceship there, which allows me to scour the entire Earth for where are the other women. So you make analogies. Things that can levitate are balloons, helicopters, and maglev trains. They do it by different methods. So you can just start pick a natural phenomenon. I picked gravity on here, and you can start making different analogies to these cases. And with each of these analogies, there's other pros and cons and limits, and that you can explore further. Now, one thing I want to point out, again, this is that whole thing where there is more than one approach. The word anti-gravity is on there. Usually when people think about this in the naive sense, that term anti-gravity, define gravity comes on. But actually that's just one small amongst those, and that specific term has a taint to it as well. So right now, just for playing some more, I'm going to take the one force fields on space itself and give you some examples. And this time in the case of flipping it around. Here, before, with our levitating spacecraft, we wanted to null out the effects of gravity for our spacecraft. Now here, in floating in space, we want to create gravity where there is none. And this, in the science fiction, there's always boggles my mind of how natural they have these synthetic gravity environments and they walk around taking it for granted. Now I know it makes filming it easier because it's studio conditions. But if you could really do that, if you had that, that would be a huge breakthrough, in which case other things on their vehicles should be using these techniques. And I tell you, when I read the first Star Trek technical manual and that their impulse drive, instead of being a version of this, which I thought it was when I was toying with these ideas as a kid, turned out to be a fusion rocket, I was so bummed. Anyway, so let's give a little example. If you have, this is one of our magic corridors where we have synthetic gravity and we have intruders. So what are we going to do? Well, how if we just turn the intensity so high that we squish it? That's one method. Okay, and what about if we disorient him by changing the direction of the field? Putting him on the ceiling or someplace else where it's hard to get through the doorways. But better yet, yeah, great, good. But what if we just kind of slap them around? Now, as fun as this was to toy with, for those who have done science and engineering, look what we've just done. Magnitude, direction, time rate of change. Those are the kind of tools that when you play with these things, it helps walk you through the math to actually get them done. You can play other games. If you put gravity on board, why not do it to move your other spacecraft? Hence the impulse drives those there. But it gets weirder. If you think, well, you're pushing it against the entire universe, well, what happened to that? Okay, so your spacecraft would go one way, the universe would go the other way, but wait a minute, that means there would have to be something more than the universe to conserve momentum. So these things trigger enough questions to where you know where to dig deeper to try and find those. I will skip the silk boat analogy. When you start distilling these down, that particular one, you discover, what are the critical issues that you need to do, and then what are the unsolved areas of physics. Now, two things I'm going to point you to there. On the space-time density, for those who know scientific notation, you'll notice that it's plus or minus 26 orders of magnitude of doubt. That's a kind of a nice way of saying we're really ignorant on that one. The quantum vacuum energy, which is actually more developed in the physics and has physical experiments for it, is plus or minus 62 orders of magnitude, which is, there's a lot of debate about how you work that in the theories. And then, like the other stuff, there's all sorts of different ways of approaching these things. There is not just one idea out there to try and approach these. Oh yeah, and some of them are dead ends. And that is what myself and a few colleagues are doing. The thing I did, actually it started on the side with NASA while I was still at NASA, this Tau Zero Foundation, where all of my more pioneering people, meaning the ones that could think outside the comfort zone of their peers and the more visionary stuff, but still keep it well grounded and do impartial, rigorous work and get publications, those people, they're cool to work with. And so finding who those were on the various topics and chipping away at these things, that was the idea. And I thought, well, I'll take my early retirement and then I will be allowed to do active fundraising. And then less than 10 months after that, DARPA and NASA Ames, DARPA is a government agency, start something called the 100-Year Starship, which blew me away because I didn't think there would be any government competition on this. So I'm still kind of dealing with that one. But we not only have scientists and engineers, but journalists and educators to help tell the story, artists and science fiction writers. As a matter of fact, David Brin's recent book, Existence, actually captures a lot of the issues that might be associated with interstellar flight. And he just constrained it to the non-faster-than-light regime. We have people spanning the really simple stuff, the solar cells, all the way to the faster-than-light. But the idea is to chip away at this in small steps. And our motto, ad astra incrementis, means to the stars in ever-increasing steps. And that, you know, in thinking about the theme here too and what you're talking about are the next steps, that's really how we accomplish things. It's just breaking the problem down and chipping away at it step by step. And that's what I got for you, and I'd love to entertain any questions, and if I could see you guys, I'd probably be asking you guys some questions too. Okay, now I'm hard of hearing. I do have hearing aids, so talk loud.
Okay, so obviously this all hinges on energy, and we're going to need energy to do any of these endeavors and various proposed solutions. I'm particularly fascinated with the idea of the Dyson Sphere, and you may be familiar with George Jaworski's recent article proposing that we could actually begin work, initial framework on actually constructing a Dyson Sphere.
Okay.
And NASA actually reached out to him after this posting saying, you know, this is legitimate, we'd like to talk. I'd be interested to hear your thoughts.
Yeah. For those who don't know what a Dyson Sphere is the idea is to build an entire enclosure around your sun so you can capture all of the energy of the sun. It's hard, but not seemingly impossible. Now, the size of space infrastructure you would need to pull that off is indeed enormous. And if you could do that, you might want to spend your time otherwise. There's something called the Kardashev energy scales of defining a situation. Level 1 is when you've mastered all the energy on your planet. And number 2 is when you've mastered all the energy of your sun. Well, if you go back to that thing and the pace of energy over the last quarter century rise, is that we won't reach the Kardashev 1 energy scale. And I define that as being able to tap all the sunlight that's just hitting the Earth until I think 3 centuries from now. I forgot what the actual value was. Now again, those estimates are based on current rates, and they could change dramatically one way or the other. You know, hopefully in the positive way. The other way of looking at the energy is that, like for the people who are looking at fusion engines, they want to mine helium-3 from Uranus. I always have to pause on that. Do I say Uranus or do I say Uranus? And Uranus is easier to say, but then you get the giggles, so you know, Uranus. Which is really hard, and that would take a lot of space infrastructure to do that. But the idea that there's other places where you can get energy that might be less work to get done than a Dyson Sphere. But the one last thing about that is at this stage, with so many unknowns, it's like, well, you consider all of them and keep an open mind about which might be which.
Have you considered the idea of having, being able to harness virtual particles that pop in and out of existence all the time, everywhere? There's been some study by, I think, an Egyptian woman.
Yeah, well, the detail with the particles that come into existence and knock themselves out. In order to have them stay in existence or get that energy, you have to put the equivalent mass energy into them, which is an enormous amount of energy. And the idea goes back to at least 1997, if not earlier. It's not a new idea. But the amount of energy it takes to do that is, you know, that basically E is equal to mc squared. So that's pretty much the easy way of describing that. How are we on time?
We got 7 minutes to hear Sean.
Okay, thank you very much.